In this video, we're going to talk about the last of our conic sections, which is the hyperbola. Now, we define the hyperbola as a locus of points such that the difference of this point P, that difference of the distance between this P to two fixed points called foci is constant. So the difference between this line segment and this line segment would be constant. If in ellipse, it's the sum. In hyperbola, it's the difference that is constant. Now, in ax squared plus cy squared plus dx plus ey plus f equals 0, the standard form of any conic, if a and c are unlike sign, meaning either this is positive or this is negative, or vice versa, this is positive and this is negative, if that happens, then what we would have is an equation of a hyperbola. Now, just like what we had on the ellipse, to get the simplest equation for the hyperbola, we place our foci at the x-axis at c0 and at negative c0. So this point here is at c0, while this point here is at negative c0. So with that now, we can see here, before that, here is our center, and from the center, that distance is from here is obviously c, and the distance to here is obviously also c. On the other hand, from the center to this point v sub 1, that is a, and from the center to v sub 2 is also a. And as we can notice, unlike in ellipse, in the hyperbola, c is greater than a, which in turn will have c squared is greater than a squared. If we transpose that, we are then sure that c squared minus a squared is a positive number, since c squared minus a squared is greater than 0. And later on, we will be using that. Now, like what we mentioned, according to the definition of the hyperbola, the distance of a point P from the first focus, from the two foci rather, that the difference of that is always constant. So let's write it down, and let's write it down as like this. We'll explain later why I made it P f sub 2 first. So their difference, the distance, is a constant T. Let's name it as T. Now, since v sub 1 is also a point on the hyperbola, so I can also say that the distance from v sub 1 to f sub 2 minus the distance from v sub 1 to f sub 1 is also the same constant. So let's take a look at what is that same constant that we can use to find the simplest equation of the hyperbola. Now, since it's a horizontal distance, as we can see from v sub 1 to f sub 2, that's a horizontal distance between points, so therefore we can just simply get the differences of their abscissas. V sub 1, since we already mentioned that the distance from the center 0, 0 is a, hence its coordinates is at a0. So the distance between v sub 1 and f sub 2 will be the difference between their abscissas. And since a is obviously bigger than negative c due to its placement in the x-axis, the distance from v sub 1 f sub 2 is represented by a minus negative c. Let's write that a bit more properly. A minus negative c. Now, the distance from v sub 1 to f sub 1 here is a bit shorter. So that is now the difference between the abscissas of the 2 points. And this time, since c is bigger than a because of its placement in the x-axis, this distance would be c minus a. So let's simplify things, and we remove now the absolute value, since we're just talking about the distance itself. So this becomes a minus negative c becomes a plus c minus c minus a equals e. We place a parenthesis because what we subtract is the entire c minus a. Now, this is negative, so we distribute that, so we become a plus c minus c plus a equals e. This is actually 0, and a plus a is 2a. So therefore, the common difference or the constant difference between the distances would always be 2a. Now, if you also notice, I always started with f sub 2. And even though we do that with p, say for example, now I'm going to have p f sub, I'm going now to derive the equation of the hyperbola. We start with p f sub 2 minus p f sub 1, this time equals 2a. I start with f sub 2 because if we draw the line, this is p, then to f sub 2, then p to f sub 1. As you can see, the distance between p to f sub 2 looks like it's longer. And in subtraction, if we subtract the longer minus the smaller or the shorter, we get a positive value. Although we can do the other way around, since we will stick with the positive value because it's easier to work with. Now, since it's not anymore v, it's now any point p, we need to now use the distance formula just like how we did it with an ellipse. So from here, the distance from p to f sub 2 would be from here, we're going to have the square root of x minus negative c squared plus y minus 0 squared. The difference of the abscissas and the square of the difference of the abscissas rather, and square of the difference of the ordinates. Minus, then we're going to do the same for p and f sub 1. That's x minus c squared plus y minus 0 squared, and this is equal to 2a. Simplifying things inside, we're going to now have the square root of, this becomes x plus c squared plus y squared, minus, this becomes the square root of x minus c squared plus y squared, and this is equal to 2a. So that it is easier for us to remove the radical sign, we transpose one of the radical expressions to the other side, leaving one of the radicals on one side. So we have x plus the square root rather of x plus c squared plus y squared would be now equal to 2 plus the square root of x minus c squared plus y squared. And this is now where we square both sides to remove one of our radicals. So from here, I now go up to here. So this gets cancelled, and I'm going now to also expand this. I'm going to have x squared plus 2cx plus c squared plus y squared is equal to, this is a binomial that we have to square, so we square the first term. It's 4a squared. Then we multiply these two terms, then multiply it to 2, and so we're going to get plus 4a times the square root of x minus c squared plus y squared. Plus this last term gets squared, so the radical gets removed, and the ones inside the radicand we can already expand it as x squared minus 2cx plus c squared plus y squared. Let's simplify things by cancelling things out that can be cancelled. We can cancel actually x squared, c squared, and y squared. And let's leave the one with the radical expression on that side and the rest moving on the other side. I'm going to have 2cx, then this becomes plus 2cx, this becomes 4cx minus 4a squared is equal to 4a the square root of x minus c squared plus y squared. It has a common factor of 4, so we can divide everything by 4. Therefore, we're going to have cx minus a squared is equal to the square root of x minus c squared plus y squared. The writing got smaller. Let's rewrite that. So we're now going to have cx minus a squared is equal to the square root of x minus c squared plus y squared. Now we square again both sides to remove the remaining radical. The left side becomes a perfect square trinomial because it's, well, a binomial. So this becomes c squared x squared minus 2a squared cx plus a to the 4th. Well, the other side, oops, sorry, I forgot a here. Let me rewrite that. There should be a here. There. This becomes now a squared times x minus c squared plus y squared when we remove the radical side. Before we distribute a squared, let's expand x minus c squared. So the left side remains the same. Let's just rewrite that. There you go. While it becomes a squared times x squared minus 2cx plus c squared plus y squared. The left side remains the same. Let's just rewrite that. Well, now we distribute a squared. Hence, we have a squared x squared minus 2a squared cx plus a squared c squared plus a squared y squared. If we're going to cancel out terms, we're going to see that we can cancel this one out. So, from there, since we cannot cancel anything anymore, that's what we'll have left. If you remember, we need to use, or we were able to see that c is greater than a. C squared is greater than a squared, so therefore c squared minus a squared is greater than 0. So we need to get a c squared minus a squared. And as you can see, if we transpose this to the other side, we can get c squared x squared minus a squared x squared. So therefore, we can get this. So let's do that. And since, let's change it to green. And since x squared is on the left side, y squared should also be on the left side. A to the fourth will be transposed to the right side. Therefore, I'm going to have c squared x squared minus a squared x squared minus a squared y squared is equal to a squared c squared minus a to the fourth. Here, we can factor out x squared. So I'm going to have c squared minus a squared times x squared minus a squared y squared is equal to, here a squared can be factored out. A squared is times a squared, not a squared, is c squared minus a squared. Since we were able to have this already, we'll let now b squared be equal to c squared minus a squared. Let's move this now. Therefore, this now becomes b squared x squared minus a squared y squared is equal to a squared b squared. We now divide both sides of the equation by a squared b squared. We can see here that b gets cancelled and this remains. X squared over a squared. Here, it's a squared that gets cancelled and this remains. So therefore, minus y squared over b squared is equal to 1. And this is the standard form of the hyperbola with, if we're going to look back at its figure, center at 0, 0, and the hyperbola opens sidewards. And just like ellipse and parabola, it has, again, different standard forms. Let's write it here. Once again, the standard forms would depend on what is the orientation of the hyperbola, whether it opens horizontally, the two curves open both left and right, or if it opens vertically, it opens upwards and downwards, and where the center of the hyperbola is. Is it at 0, 0, or is it at hk? What we were able to derive is the hyperbola opens horizontally with center at 0, 0, and that would be x squared over a squared minus y squared over b squared equals 1. If the center is not at 0, 0, it's at hk, then we say that x minus h squared over a squared minus y minus k squared over b squared equals 1. Now, one main difference between the hyperbola and the ellipse is that if in the ellipse, a squared can be moved to any denominator, here, a squared will always be on the term that is positive, the term that is usually written first. So, if we want to write it vertically, it's not a squared that will move. Instead, it will become y squared over a squared minus x squared over b squared equals 1. If it's hk, this becomes y minus k squared over a squared minus x minus h squared over b squared equals 1. So as you can see, whichever variable is the positive one, it tells us the orientation of the hyperbola. If it's x squared that is positive, it's horizontal. If it's y squared that is positive, it's vertical. Also, we were able to show that b squared is equal to c squared minus a squared. But since c squared is not in the standard forms, we need to solve for that. So if transposing a, we're going to get a squared plus b squared is equal to c squared. Now, why does that look like the Pythagorean theorem? Let's go back to the figures here. A squared, b squared, ABC here actually forms a right triangle. That's why the equation looks like a Pythagorean theorem, because they actually follow the Pythagorean theorem. So going back, here now are the different standard forms of the equation of the hyperbola. Now let's look at the different parts of the hyperbola that we're going to look for. So of course, we start at our center, whether it's 0, 0 or whether it's hk. And then we now look at our equation to determine whether it's horizontal or whether it's vertical, because that will now tell us where to move when we're going to look for other parts. Now that we know, or now that we figured out how the orientation is in the center, we then go to a squared, b squared, and c squared. Remember, a squared is always under the positive term, and the positive term is almost always written first. Then b squared is the one written under the negative term. And c squared will be a squared plus b squared. Then we get a, b, and c because we use their measurements. For a, from the center, we move here. That's a units. Not right here. Here you go. And here, it's also a units. And those 2 points, v sub 1, v sub 2, are the vertices of our hyperbola. So they're related with the value of a. Also, this line segment here, which I'm going to make it yellow. It's not seen, but maybe let's make it red instead. Here, that line segment that passes through the center with endpoints at the vertices is what we call, okay, let's just take it back. What we call our transverse axis. So if it ellipse, it's the major axis. In the hyperbola, it's the transverse axis. And as we can see, since that's a and a on both sides, the length of the transverse axis is 2a. Now, for b, the distance now, as you can see, this is b. From the center to this point here, that's 0, negative b. And this point here is 0b. But those points are not on the hyperbola, as you can see. But still, they are parts that we look for, and they are the co-vertices of the hyperbola. Now, this line segment here, I'm going to make it in green. This line segment here, oops, there you go. There you go. That green line segment here with this point here and that point there that passes through the center, perpendicular to the transverse axis, and the endpoints or the co-vertices are what we call the conjugate axis, which is the equivalent of the minor axis in the ellipse. In the hyperbola, it's called the conjugate axis. And similarly, that is b, and this is also b, so the length of the conjugate axis is 2b. Now, from the center to the foci, that's the measure, that's c units here, c units. So c is related to the foci. Now, one other difference that we can see here is that, as you can see, the transverse axis, the red line segment, is just until the vertices. The major axis in the ellipse covers or intersects the foci, but the transverse axis does not. They're just aligned, they're just collinear, but the transverse axis does not cover, does not touch, does not intersect the foci. Now, since we're already in the foci, of course, we also have these line segments. I'll use blue. We also have these line segments that passes through our foci and whose endpoints are on the curves of the hyperbola. And those are the endpoints of our latera recta. And it's still the same, we will have b squared over a with them. So this length is b squared over a, and so does this. So we had b squared over a on the coordinates of the foci, whichever it would be. At the same time, the length of each latus rectum is 2, b squared over a. What is new, however, in these parts would be these two lines here. I'm going to highlight them in red. This line here and this line here. Those two lines are the asymptotes of our hyperbola. And the asymptotes are, the first thing that we need to them is their slope, which we compute by getting b over a if the hyperbola opens horizontally, and the slope is a over b if it opens vertically. The asymptotes, rather, are not part of the hyperbola, but they are guides in graphing the hyperbola apart from the vertex and ELRs. So, for the asymptotes, we're going to get the equation. If the center is 0, 0, it's simply y is equal to b over ax, one with positive slope, and its negative slope. Y is equal to negative b over ax. That's why some books write it as y is equal to positive or negative b over ax. If it's vertical, then it becomes y is equal to a over bx, y is equal to negative a over bx, or y is equal to positive or negative a over bx. Once the center is not anymore at 0, 0, it's in hk, then y and x will have that k and h. So for example, it now becomes, this becomes y minus k is equal to b over a times x minus h. Which later we can show in the other parts of the slide. Now, another thing to emphasize is that when we draw the asymptotes and the hyperbola itself, you notice this square here. This square here is made up, or at least it's guided by the vertices and the co-vertices. This square here that we make in its corners, the asymptotes should pass through. Of course, through the center as well. So that's a guide, especially when our asymptotes become too complicated to be graphed. Now, just to show the formulas, here are the formulas of the hyperbola if the center is at 0, 0. And here are the set of the hyperbolas of the set of formulas for the hyperbola if the center is at hk. Like what I mentioned a while ago, if it's at hk, this becomes the equations of the asymptotes.